Hello fellow problem solvers. So today we're going to be doing a problem from the 2013 IMO, problem number 1. I suggest you try this problem out for a minimum of 45 minutes, ideally 2 hours, but not more than 4 hours. If on the other hand you would like to go along with us, I suggest you take 20 minutes and play around with the problem. This is the first problem solving strategy that we will use to solve this problem. So let's begin. So the problem is self-explanatory. We are given k and we are given n as positive integers, and we must find k positive integers m1, m2, mk such that this is true. So the first order of business here is really playing around with the problem. This means trying to find solutions for specific values of n and k. Playing around with small cases is a fundamental problem-solving strategy because you can get ideas from small cases. When I first solved this problem, I probably played around and found solutions for at least 50 pairs of numbers k and n before I generalized it and solved the problem. So now I invite you to take 15 minutes and play around, find solutions for small values of n and k. That's what we're going to be doing now. So playing around with k equals 1 is trivial, but k equals 2, when we play around with specific values of n, we get, for n equals 1, we get 2 over 1 times 2 over 1, which is we get 1 and 1 as solutions. Then for 2, we get 4 and 1 as solutions. Then we get 3 and 2, 6 and 2, 5 and 3, 8 and 3. Now take a minute and see, do you notice any pattern here? And what you may notice is that we get 2 over 1, 2 over 1, then 3 over 2, 3 over 2, 4 over 3, and 4 over 3. And it only makes logical sense to guess that we might get for n equals 7, 10 over 9 as being 5 over 4 times what anything else we need. I mean, 10 over 7 is equal to 5 over 4 times what else do we need? Well, we need a 7, 8 sevenths. And this actually turns out to be a solution. Now the question is, can you take a minute or two to find a general pattern here, to actually describe it algebraically? Now what you may notice also in this pattern is when we have odds up top, we get the same odd, and when we have the odds on the bottom, we get the same odd on the bottom. Odds up top, odds on the bottom. This hints that we may need to separate even and odd n. And in fact, for n equals 2t plus 1, what we have is 2t plus 4 over 2t plus 1 is equal to 2t plus 1, 2t plus 2 times t plus 1, t plus 2. Because here t plus 1 and twice t times 1 cancel out, and we're left with 2 times t plus 2, which is 2t plus 4 and 2t plus 1 on the bottom. And for n equals 2t, we have 2t plus 3 over 2t is equal to 2t plus 3 over 2t plus 2 times t plus 1 over t. So this solves k equals 2 and every single n. Now we play around with k equals 3, 4, and 5. For k equals 3, you may find in some cases there are multiple solutions, but I just wrote out the first 8, which had some interesting pattern for me. Can you spot it? Take a minute to try and spot the pattern. Well, the pattern is we have the same pairs of, say, b and c, for consecutive odds than evens. It's the same pair. That's one thing you may notice. And the other thing you may notice is we always get rid of, so to speak, of the odd number first. And then we have the same pattern for the evens and odds. So now I would ask you to take 3 to 7 minutes and try to generalize this. Before I show you the solution, notice that we would have to separate out the even n and the odd n. Now comes the solution. And the solution is basically this. For n equals 2t plus 1, we write the solution as 2t plus 1 being one of the m's. And then we're left with t plus 4 over t plus 1, which we have solved already because we solved the case k equals 2. And k equals 2 is just these two numbers, the denominator and the numerator, being separated by 3. Now for the evens case, we get 2t plus 7 over 2t is equal to 2t plus 7 over 2 times t plus 3, i.e. the first m is 2t plus 6 times t plus 3 over t, which we also have by induction. And now you can see also why we had the same pattern for evens and odds that were consecutive. Notice that if this was 2t minus 1, we would get t plus 3 over t here, and the same here, i.e. we would get the same solution. Now, this is the point where I would invite you to, by yourself, try to come up with the solution for 4 and 5, and then try to finish the problem on your own. I invite you to take 10 to 20 minutes to try and do this. And while you're doing this, I'll give you a hint. Think inductively. So now I'm going to move on to the case 4 and 5. So the case k equals 4 is really trying to show that n plus 15 over n is the product of 4 numbers of the form 1 plus 1 over m, where m is a positive integer. Now what you may have found out just by playing around is that this also follows the same pattern for evens and odds, meaning they are different solutions, and they are that if n is 2t plus 1, then we have that the thing up top is twice n times 8, and on the bottom we have 2t plus 1. And now we write this as 2t plus 1, 2 times t plus 1 times t plus 8 over t plus 1. And t plus 8 over t plus 1 we already have via the case k equals 3. We know we can write this as the product of 3 numbers of the form 1 plus 1 over m. So now that this solves the odds case, if n is even, i.e. of the form 2t, then the whole expression becomes 2t plus 15 over 2t is equal to 2t plus 15 over 2 times t plus 7 times t plus 7 over t. And this t plus 7 over t is done by the previous case k equals 3. So now this solves the case k equals 4. Now let's go on to k equals 5. What we have in this case is we need to represent n plus 31 over n. And it's the same idea that you may try right away, which is break it down into the odd and even case. And let's try the same sort of pattern that worked before. For odds, we'll write this as 2 times t plus 1 over 2t plus 1 times t plus 16 over t plus 1. And we have this because we solved k equals 4, which means we know we can write this as the product of 4 numbers of the form 1 over m, where m is a positive integer. Now for the other case, it would be a shock if it didn't work by writing it as 2 times t plus 15 over 2 times t plus 7 times the fact that this is not correct. We messed up the case. It's actually 2t plus 31 over 2t is equal to 2t plus 31 over 2 times t plus 15. And what we're left with is t plus 15 over t, which we know we can solve because we solved k equals 4. So here we are done, just like in here. Now is the time to pause for 5 to 15 minutes and bring it all together and solve the problem. Let's do that now. So the way we would formally prove this is via induction on k, which is basically what we've been doing. So for our base, we know that this is true for k equals 1, 2, 3, 4. And let's assume it's true for all k till some L. And now we try to prove that the claim is also true for k equals L plus 1. So let's recap. What does it mean for the claim to be true for k equals L? Well, it means that there are L integers, m1, m2 till ml, such that n plus 2 to the L minus 1 over n has a solution of the form that we want, 1 plus 1 over m1 all the way till 1 plus 1 over ml. So now we divide the k equals L plus 1 case into two subcases. If n is odd, of the form 2t plus 1, then what we need to prove is that there exists integers such that we'll have 2t plus 1 plus 2 to the L minus 1 over 2 to the t plus 1, which is equal to 2 times t plus 2 to the L minus 1 over 2 to the t plus 1. And this thing right here is going to be equal to 2t plus 1, 2 times t plus 1, times t plus 2 to the L minus 1 over t plus 1. And now this, we know we can solve with L of these integers m, because that is true by the inductive hypothesis. So this case is done. Now, if n is of the form 2t, where t is a positive integer, what we have is that this whole thing rewrites as 2t plus 2 to the L minus 1 over 2t is equal to 2t plus 2 to the L minus 1 over 2 times t plus 2 to the L minus 1 minus 1. And we need to multiply this by t plus 2 to the L minus 1 over t. Now this thing right here is of the identical form as this. Actually, we made a mistake. This should have been L plus 1 and then just plain L. And this should have been L plus 1, and just plain L. Now everything's in order, and we have proved that this can be written as the product of L plus 1 numbers of the form 1 over m, where m is a positive integer. This finishes up the problem, and as always, thanks for problem solving.